Global Positioning System. In the previous chapter, we have discussed about the different types of data query and how important is a data query in data analysis and decision support system. In this chapter, we will discuss about Global Positioning System. Objectives. Global Positioning System is used in data capture and also used in data entry methods. It is largely utilized by the common people for navigation system. In this chapter, we will understand about definition of GPS, evolution of GPS, dilution of precision, GPS segments or principles of GPS, that is control segment, space segment, user segment and functions of GPS. Definition of GPS. The GPS is a satellite-based navigation system made up of a network of 24 satellites placed into an orbit by US Department of Defense. GPS was originally intended for military applications, but in 1980s, the government made the system available for civilian use. GPS works in any weather conditions anywhere in the world, 24 hours a day. There are no subscription fee or setup charges to use GPS. The Global Positioning System is a satellite-based navigation system consisting of a network of 24 orbiting satellites that are 11,000 nautical miles in space and in 6 different orbital paths. The satellites are constantly moving, making 2 complete orbits around the Earth in 24 hours, that is 2.6 kilometers per second. The Global Positioning System GPS originally is called 𝗪star GPS, is a satellite-based radio navigation system owned by the United States government and operated by the United States Space Force. It is one of the global navigation satellite system that provides geolocation and time information to a GPS receiver anywhere on or near the Earth where there is an unobstructed line of sight to 4 or more GPS satellites. Obstacles such as mountains and buildings block the relatively weak GPS signals. The Global Positioning System in a space-based navigation and positioning system that was designed by the US military to allow a single soldier or a group of soldiers to autonomously determine their position to within 10 to 20 meters of truth. The concept of autonomy was important in that it was necessary to design a system that allows the soldier to able to determine where they were without any other radio or otherwise communications. The GPS project was started by the US Department of Defense in 1973, with the first prototype spacecraft launched in 1978 and a full constellation of 24 satellites operational in 1993. Originally limited to the use by the United States military, civilian use was allowed from 1980s following an executive order from President Ronald Reagan. The system provides critical capabilities to military, civil and commercial users around the world. It is maintained by the United States government and is freely accessible to anyone with a GPS receiver. Evolution of GPS. Like so many other high-tech developments, GPS is maintained by the United States government and is freely accessible to anyone with a GPS receiver. During the late 50s and early 1960s, the US Navy sponsored 2 satellite-based positioning and navigation system, Transit and 𝗙mission. The Transit system became operational in 1964 and was made available to the public in 1969. 𝗙mission was a prototype system that never left the ground. Simultaneously, the US Air Force was conducting concept studies for a system called the System 621B. The ground tests were performed to validate the concept, but before the system could be implemented, the US Deputy Secretary of Defense in April 1973 designated the Air Force as the Executive Service 𝗘𝗂𝗨𝗡𝗔 and 621B systems into one single defense navigation satellite system. From this emerged a combination system concept designated the 𝗪𝗧, Navigation System with Timing and Ranging, Global Positioning System, or simply GPS. The 1970s saw the implementation of Phase 1, the concept validation phase, during which the first prototype satellites were manufactured and tested. In 1973, decision to develop a satellite navigation system for military. In 1974 to 1979, conducted system test US Air Force and Navy. The first functional 𝗪𝗧 prototype satellite launch occurred in June 1977 and was called NTS-2, Navigation Technology Satellite, which was actually a modified 𝗕𝗎tion satellite. While the NTS-2 only served some 7 months, the concept was shown to be viable, and in February 1978, the first of the Block 1 𝗪𝗧 satellites was launched. In 1977, first receiver test was conducted without placing the satellite in the orbit. Signal received from the pseudo satellites. The concept started in the late 1960s, but the first satellite was launched in February 1978. In 1979, Phase 2 full-scale development and testing of the system was implemented with 9 more Block 1 satellites launched during the following 6 years. This was followed in late 1985 by Phase 3, a full-scale production and deployment of next generation of Block 2 satellites. In 1978 to 85, a total of 11 Block 1 satellites were launched. In 1979, decision to expand GPS with 18 satellites in space. In 1980 to 82, financial crisis occurred when the sponsors questioned the usefulness of the system. In 1983, civilian use of GPS was allowed after Soviet Union shot down Korean airplane that got lost over Soviet territory. In 1986, GPS program suffered a setback due to the accident of the Challenger, which was supposed to carry Block 2 satellites to the orbit. Then Delta rockets were used for this purpose. In 1988, the number of satellites were increased to 24. In 1989, first Block 2 satellites were installed and activated, and the 𝗪𝗏𝗏 introduced the first hand-held GPS receiver. In 1990 to 1991, temporal deactivation of 𝗧 during Gulf War. In 1992, GPS was used in Operation Desert Storm. 1993, initial operation capability was announced and decided worldwide civilian use free of cost. In 1994, last Block 2 satellites complete the satellite constellation. In 1995, fully operational capability was announced. On March 1996, the President decided to make GPS free for civilian users. In 2000, final deactivation of 𝗧 to give positional accuracy of 20 meters from 100 meters. In 2005, launching of the second RM GPS satellites that supports the new military M signal and second civil signal L2C. GPS project was developed in 1973 to overcome the limitation of previous navigation systems, integrating ideas from several predecessors, including a number of classified engineering design studies from 1960s. The current system became operational on June 26, 1993, when the 24th satellite was launched. Bradford Parkinson, Roger L. Easton and Ivan A. Getting are credited for inventing the GPS. DOP, dilution of precision. DOP is a value that shows the degree of degradation of GPS positioning accuracy. The smaller the value is, the higher the positioning accuracy is. This value depends upon the position of the GPS satellites tracked for positioning. If the tracked satellites spread evenly over the Earth, the positioning accuracy would become higher, and if the positions are tracked satellites are disproportionate, the position accuracy would be lower. GPS segments or components of GPS or principles of GPS. Global positioning system consists of three major segments: the space segment, the control segment, and the user segment. The space and control segments are operated by the United States military and administered by the US Space Command of the US Air Force. Basically, the control segment maintains the integrity of both the satellites and the data that they transmit. The space segment is composed of the constellation of satellites as whole that are currently in orbit, including operational, backup, and inoperable units. The user segment is simply all of the end users who have purchased any one of a variety of commercially available receivers, while the user segment obviously includes military users. This will concentrate on the civilian users only. Control segment. The control segment of the global positioning system consists of one master control station MCS located at Falcon Air Force Base in Colorado Springs, Colorado, and 4 unmanned monitor stations located strategically around the world. Example: Hawaii Monitor Station, Ascension Monitor Station, Diego Garcia Monitor Station, Kwajalein Monitor Station. In addition, the Air Force maintains 3 primary ground antennas located more or less equidistant around the equator. Observation and controlling the satellite system regularly to check the satellite functions and its accurate position in the space, to determine the time of GPS, update periodically navigation messages for each satellite. In the event of some cartographic failure, there are also 2 backup master control stations, one located in Sunny Valley, California, and the other in Rockville, Maryland. The unmanned monitor station passively track all GPS satellites visible to them at any given moment, collecting signals, ranging data from each. This information is then passed on to the master control station at Colorado Springs via the secure DSCS, Defense Satellite Communication System, where the satellite position, ephemeris, and the clock timing data, more about these in the later session, are estimated and predicted. The master control station then periodically sends the corrected position and the clock timing data to appropriate ground antennas, which then upload those data to each of the satellites. Finally, the satellite use that corrected information in the data transmission down to the end users. This sequence of events occur every few hours for each of the satellites to help ensure that any possibility of the error creeping into the satellite positions or the clock is minimized. The CS is responsible for maintaining the satellites and their proper functioning. This includes maintaining the satellites in their proper orbital position called station keeping and monitoring satellite subsystem health and status. Newly added control station after 2005 are Washington DC, England, Ecuador, Argentina, Bahrain, and Australia. These monitor stations measure signals from the satellite vehicles which are incorporated into the orbital models for each satellite. Master stations collect the data about the satellites of this system continuously from the other tracking stations. Master control segment processes the tracking data for computation of satellite ephemerides or coordinate and satellite clock parameter. The master control station uploads ephemeris and clock data to the satellite vehicles. The satellite vehicles then send subset of the orbital ephemeris data to GPS receiver over radio signals. The MCS also monitor the position of satellites at any instant of time. The functional capability of satellites and variation of the navigation data. The computation of satellite ephemeris and the clock errors are most important task of control station, as both variables are important to get high accuracy. The space segment consists of the complete constellation of orbiting 𝗪 GPS satellites. There were 11 Block 1 prototype satellites launched, 10 successful, followed by 24 Block 2 production units. Currently, only one Block 1 satellite is still operational, while 4 Block 2 backups remain in ground storage. The base size of the constellation includes 21 operational satellites with 3 orbiting backups, for the total of 24. They are located in 6 orbits at approximately 20,200 km altitude. Each of the 6 orbits is inclined 55 degrees up from the equator and is spaced 60 degrees apart, with 4 satellites located at each orbit. The orbital period is 12 hours, meaning that each satellite completes 2 full orbits each 24 hours day. The space segment is the constellation of satellites from which users make ranging measurements. The satellite vehicles transmit a PRN coded signal from which the ranging measurements are made. This concept makes GPS a passive system for the user, with signals only being transmitted and the user passively receiving the signals. The space segment of the system consists of GPS satellites. The space vehicles send radio signals from space. The space segments consist of the group of minimum 24 satellites and the signals that are broadcasted by them, which allow the user to determine position, velocity and time. The basic function of the satellite are to receive and store data uploaded by control segment, maintain accurate time and means of an onboard automatic clocks, and transmit information and signals to the users on 2 L-band frequencies. Out of 52 constellation of GPS satellite, the 11 were launched as an experimental satellite in Feb 1978 under the so-called Block 1 phase. Block 2 and Block 2A were launched from 1989 onwards. Full operational capability was declared on 17 July in 1995. Currently, 12 of these satellites are redesigned as part of GPS modernization program. GPS satellite details. User segment. This user segment consists different characteristics which are included as name, 𝗪, the navigation satellite, timing and ranging USA. Galaxy consists of 24 satellite. The manufacturer of this is Rockwell International. The altitude the user segment or the satellite is present is 20,200 km and the weight of the satellite is 845 kg and the number of path or orbits are 6 and the number of satellites per path are 4. The orbital inclination is 55 degrees to equatorial plane. Orbital spacing is 60 degrees. Orbital period 12 hours. The planned lifespan of each satellite is 7.5 years. Information that comes from space and sends to satellite is the most important part of GPS. The part that does this work is user segment. It has the GPS receiver section. The GPS collects and stores all the information that has come from space. For this, 4 satellites are required. The GPR user segment consists of the GPR user and the user community. GPS receiver convert the SV signals into position, velocity and time estimates. 4 satellites are required to complete the 4 dimensions of X, that is latitude, and Y, that is longitude, and Z, altitude, and T, time. GPS receivers are used for navigation, positioning, time dissemination and other research. The user receiving equipment comprises the user segment. Each set of equipment is typically referred to as a GPS receiver, which processes the L-band signals transmitted from the satellites to determine the user PVT, that is position, velocity and time. While the PVT determination is the most common use, receivers are designed for other applications such as computing user platform altitude, that is heading, pitch and roll, or as a timing source. Navigation in the 3 dimension is the primary function of GPS. Navigation receivers are made for aircrafts, ships and ground vehicles and for hand carrying by individuals. Precise positioning is possible using GPS receiver at reference locations, providing correction and relative positioning. Geodetic control and plate tectonic studies are example. Time and frequency dissemination based on the precise clock on the board the SVs and controlled by the monitor station is another use of GPS. Astronomical observatories, telecommunication facilities and laboratory standards can be set to precise time signals or control to accurate frequencies by special purpose GPS receivers. Research projects have used GPS signals to measure atmospheric parameters. Working functions of GPS. Generally, the functions of a GPS are completed with 5 steps. Step 1. Triangulation from satellites. Step 2. Measuring distance from a satellite. Step 3. Getting perfect timing. Step 4. Knowing where a satellite is in space. Step 5. Correcting errors. Step 1. Triangulation from satellites, which is the GPS operation is based on the concept of ranging and trilateration from the group of satellites, which act as precise reference points. Each satellite broadcasts a navigation message that contains the following information: a pseudo-random code called a course acquisition (CA) code, which contains orbital information about the entire satellite constellation, almanac. Detail of the individual satellite positioning, that is ephemeris, that includes information used to correct the orbital data of satellites caused by small disturbances. The GPS system time derived from an atomic clock installed on the satellite with clock correction parameters for the correction of satellite time due to differences between the UTC and GPS time, the occasional leap second added to a year, and delays predicted by a mathematical ionospheric model caused by the signal travelling through the ionosphere. A GPS health message that is used to exclude unhealthy satellites from the position solution. GPS receiver in the aircraft takes 12.5 minutes to receive all the data frames in the navigational message. Once obtained, the receiver starts to match each satellite's CA code with an identical copy of the code contained in the receiver's database. By shifting its copy of the satellite's code in a matching process and by comparing this shift with its internal clock, the receiver can calculate how long it took the signal to travel from a satellite to the receiver. The distance derived from this method of computing distance is called a pseudo range, because it is not a direct measure of distance but a measurement based on time. Pseudo range is subject to several error sources, including atmospheric delay and multipath errors. but also due to the initial differences between the GPS receiver and satellite time references. Using a process called trilateralization, the GPS receiver then mathematically determines its position by using the calculated pseudo ranges and the satellite position information that has been supplied by the satellites. GPS 3D trilateralization: if only one satellite is visible, position location is impossible, as the receiver location can be anywhere on the surface of a sphere with the satellite at its center. If two satellites are visible, the receiver location can be anywhere on a circle where the surface of the two spheres intercept. So, position location is also impossible. When a third satellite becomes visible, the GPS receiver can establish its position as being at one of the 2 points and previously derived circle where the third satellite sphere intercepts it. So, whilst position fixing is possible, it is unreliable unless it is assumed that the receiver is at sea level on the surface of the earth, because it is almost certain that only one of the 2 derived points would be near to the surface of the earth. So, fixing is possible, but only in 2 dimensions, 2D fixing in latitude and longitude. With at least 4 satellites visible and their alignment good, the 4 spheres will be intersect at only one point in space. So, the receiver position can be accurately fixed in the 3 dimensions, 3D fixing, that is in latitude, longitude and altitude. With 5 satellites visible, it is possible for the system to automatically detect an erroneous signal. With 6 satellites visible, it is possible for the system to automatically detect an erroneous signal, identify which satellite is responsible and exclude it from consideration. Altitudes derived from GPS position are known as geodetic altitudes and were not initially used for aircraft navigation. PBN requires that they and the navigational information presented by the system are based on the World Geodetic System established in 1984. The World Geodetic System 84 coordinate system, as the GPS satellites provide a very accurate time reference as well as precise 3D position fixes, they can also calculate and provide accurate speed data. Step 2. Measuring distance from a satellite. Normally, distance are calculated on GPS is based on signal of the satellite ranging. The easy formula to calculate the distance is distance d is equal to speed of the satellite range, that is 3 into 10 to the power of 8 meter per second into time. Time is equal to T2 minus T1, where T1 is the sending time and T2 is receiving time. Step 3. Getting perfect timing. If travel time measures through the radio signal are the basics of GPS, then stopwatch are very working instrument in this case. If the time is stopped for 1,000th of a second, then it will wrong at 200 miles. In terms of satellites, timing is perfect because the atomic clock is compulsory element of satellite system. The key to accurate scheduling is to measure the distance to an extra satellite. If the 3 exact measurements can identify the 3-dimensional position, then the 4th incorrect measure does the same thing. Step 4. Knowing where a satellite is in space. We assume that we know the exact position of satellites, for which we can use that satellites as a reference point. But how can we know that exactly where they are? After all, they float in space of 11,000 miles. Step 5. Correcting errors. So far, the calculation we are pointing to a GPS, that is sporadically, as if whole thing was happening in a vacuum. But in reality there are a lot of things which can be disrupt the GPS signals. To get the accurate results, this error likely to be corrected. For example, the ionosphere and atmosphere may be a reason for delay the whole function. Some error can be factored out by using arithmetic calculation and model. The relative position of the satellite in the sky can give rise to another errors. Summary. The global positioning system is a network of 24 satellites. GPS works in any weather condition. The global positioning system has components like control segment, user segment and space segment. The functions of GPS consist of triangulation of satellite, measuring distance from satellite, getting perfect timing, knowing where is the satellite in the space and correcting errors.